Chemistry. Today we are going to discuss about isomerism. Here, according to our syllabus, we will discuss about the basic two types of isomerism, that is structural isomerism and stereoisomerism. Structural isomerism is further subdivided into five main branches, that is chain isomerism, position isomerism, and functional group isomerism. That will be discussed there, but two more types of structural isomerism are metamerism and tautomerism. We will not discuss, but, you just have to know the names of these two types, tautomerism and metamerism. Secondly, we will discuss about stereoisomerism. Stereoisomerism would be due to the space orientation of the atoms bonded to the different carbons, which is further subdivided into two main categories, that is geometrical isomerism or cis-trans isomerism, and second is optical isomerism. We are going to discuss all of these in detail. Let us start from isomerism definition. What is isomerism? Isomerism is actually the phenomena in which one or more than one compounds have same chemical formula but different chemical structures. Let's see, here we have example of propene and cyclopropane. Both have same chemical formula C3H6, but both are different compounds. This belongs to alkene and this belongs to alkanes. Okay. Isomerism, as we already have discussed, is further subdivided into two main categories, that is structural isomerism and stereoisomerism. First of all, we are going to discuss about structural isomerism. Structural isomers are the compounds. Structural isomers are the compounds that have same molecular formula, but different structural formula. This is further subdivided into three main categories. This example is actually from chain isomerism, in which length of the chain is variable but the compound or chemical formula of the compound remain same. In both of these compounds, the structural formula is C4H10. Similarly, in this compound, C4H10. Both of these structures have same chemical formula but different structures. Structural isomerism is further subdivided into three main categories, that is chain isomerism, positional isomerism, and functional group isomerism. First of all, we are going to have a look on chain isomerism. In chain isomerism, compound have same molecular formula, but what is the difference? But their longest hydrocarbon chain is not the same. As we have discussed in our above example, that is N-butane and 2-methyl propane, both are actually butane with having C4H10 chemical formula. Here we are given an example pentane and 2,2-dimethyl propane. Both the structures have C5H12 chemical formula. C5H12 chemical formula. But what is the difference? In both the structure, the difference is of the longest hydrocarbon chain. Here, the hydrocarbon chain is consistent of 5 carbons, but here the longest carbon chain is 3 carbon longest chain. This type of isomerism in which variation or variation of the length of the hydrocarbon chain is called chain isomerism. Next is positional isomerism. This isomerism arises due to the position of functional group in each isomer at different carbon. Let us see, we are given an example of butanol. In this structure, functional group OH is present at carbon 1. This is carbon 1 and functional group is present at carbon 1. That's why we are calling it 1-butanol. And for this structure, it is 2-butanol because OH functional group is attached at carbon number 2. So positional isomerism is due to the difference of position of functional group on the hydrocarbon chain. Next is functional group isomerism. In functional group isomerism, chemical have same formula but different functional group. Let us see, here we are given 1-butanol which have chemical formula C4H10O. Similarly, this is an ether compound C4H10O, but we are unable to differentiate from the chemical formula that both have different class of organic compound. This compound is from alcohol. This compound is from ether family. So such kind of isomerism that arises due to the difference of functional group is called functional group isomerism, and in both the classes there will be both physical and chemical properties variable from each other. This was the brief introduction of isomerism, of structural isomerism, in which we discussed chain isomerism, position isomerism, and functional group isomerism. Now we are going to word stereoisomerism. Then what is stereoisomerism? Stereoisomerism or stereoisomers are the compounds that have same atoms connected to each other. Atoms connectivity is same, but what is the difference? Atoms are differently arranged in space. Their space orientation is different. Okay. So we can say that stereoisomerism is the type of isomerism that arises due to the space orientation, different space orientations of the atoms in a compound. Similarly, stereoisomerism is further subdivided into two main categories, that is geometrical isomerism or cis-trans isomerism, and then optical isomerism. Let's see geometrical isomerism. What is geometrical isomerism? Geometrical isomerism actually results from a restriction in the rotation about double bond or a ring compound. We will see the examples in both situations, uh, cis-trans or geometrical isomerism in double bond or in ring compound. As carbon-carbon or ring structure is formed, carbon-carbon double bond structure or ring structure is formed, rotation of the atoms bonded to that carbon is restricted due to that double bond or ring structure. So this restriction in rotation gives specific structure to the compound. This type of structures can be cis or trans. What is cis structure? In cis structures, cis isomers have functional group on the same side of the double bond or ring carbon. Let's see, this is a compound. These two, if these two are on the same side, it would be cis structure. Or if are at opposite side, like this, and this. Okay, this is trans structure. Functional group on the same side of the double bond, then the structure would be cis. Trans form have functional group on the opposite sides of the double bond. Okay, then it would be trans form. Both the compounds have different chemical and physical properties. Cis and trans structures have different physical and chemical properties, like melting point, boiling point, physical properties, and their reactivity is from their chemical property. Geometrical isomerism in unsaturated compound or due to double bond. This is an unsaturated compound due to the presence of that double bond. If both the functional group are on the same side of a functional group, then it would be cis structure. Cis 1,2-ethane diol. If both the functional group are on the opposite side, then the structure would be trans. This was geometrical isomerism in unsaturated or double bond compound. Now we are going to see the geometrical isomerism in cyclic or ring compound. Let us see, this is the cyclohexane derivative of alcohol, in which two alcohol group are substituted. In this structure, both the OH functional group are above the ring, and in this structure both the OH functional group are below the ring. So it means this structure can be written like that: both the OH functional group are above the ring, it would be cis structure. If both OH functional group are below the ring, then it would be also a cis structure, because rotation is not possible in the ring. So both the OH functional group will remain below the ring. Now let's move to the trans structures of the. This is a trans structure. Trans 1,4-cyclohexadiol. This is a cyclohexane, which is derived derivative of OH functional group both on. This OH functional group is above the ring, above, and this OH is below. So the structure can be written like that: OH functional group above the ring and OH functional group below the ring. Similarly, it is a trans structure. It is also a trans structure in which this is below the ring and this OH is above the ring. So we can write this structure like that: this OH is above, below, or this OH is below the ring. This was the geometrical isomerism that rises due to the restriction of rotation of bond due to the presence of ring structure or double bond or unsaturation. Last type of isomerism is optical isomerism. That is the second type of stereoisomerism. What are optical isomers? And what is the optical isomerism? Isomers that differ in their behavior toward the plane polarized light when passed through them is rotated clockwise or anti-clockwise. These are actually those compounds in which at least one carbon is bonded to four different groups or four different atoms. Like in this compound, this carbon is attached to four different groups. Let's see, this is hydrogen, this is CH2OH, this is OH, and this is CHO. All the four groups are different. So such carbon that is consist of four different groups, or that is bonded to four different groups, is called chiral carbon. Due to this character or chirality, when the plane polarized light is passed through such type of structures, light is rotated either clockwise or anti-clockwise. If it is rotating the plane polarized light in clockwise direction, then the compound would be called as dextrorotatory. Dextro. If it is rotating the plane polarized light in anti-clockwise direction, then it would be called as levorotatory. And such phenomena of showing different behavior toward the plane polarized light is called optical isomerism. Here is the example of glyceraldehyde. In this glyceraldehyde is dextrorotatory. This is levorotatory. Now there is a question how we will decide which compound would be dextrorotatory or which would be levorotatory. For determining this character, we have to arrange these numbers in a sequence. Then we have to note that sequence, either that sequence is anti-clockwise or it is clockwise. Let's suppose this carbon is bonded to 4 different groups. Which group have higher atomic number atom that is directly attached to this carbon? This is oxygen. Oxygen's atomic number is 8. So it would be given as positive 1. Then we have to check which structure would be given the name carbon. This is carbon. Then carbon is attached to hydrogens. If this structure is giving anti-clockwise rotation, anti-clockwise numbering, then we will call it as levorotatory or L structure. If the structure is giving such type of rotation of the sequence, last number is not counted in determining the sequence, then it would be D. Dextrorotatory or okay, sorry, both are in the same direction. This structure, then we will move toward this way. It is dextrorotatory. Optical isomers, its further detail will be given in A2 part. So you have to wait up till then. Optical isomers arise when a carbon atom in a molecule is bonded to 4 different groups. That carbon atom is called chiral center. Due to the presence of this chiral center, when this compound is seen in mirror, it looks like that. This is the lactic acid formula. Lactic acid, when it is placed in front of mirror, it forms a mirror image like that. These two groups will remain at their own position, but these two groups will exchange their position. Both these structures are optically active and will form enantiomers. For chirality or for optical activity, the compound must have chiral center and must have non-superimposable mirror image of each other. Then there would be enantiomers of each other. This lactic acid enantiomer and this lactic acid isomer or this isomer would be both will be enantiomers of each other. I hope it would be helpful for you in your preparation. So thank you. Have a good day.